Earth's climate is a vast and intricate system shaped by the interplay of air, water, land, ice, and life itself. To understand how the climate functions, imagine the planet as a carefully balanced orchestra. Each section, air, water, land, ice, and living things, plays its part, sometimes in harmony, sometimes in tension, but always influencing the overall performance. These components, known as the atmosphere, hydrosphere, cryosphere, lithosphere, and biosphere, interact constantly, producing the environments we know and shaping the conditions that make life possible. The engine that powers this orchestra is the sun. Every moment, the sun bathes Earth in a stream of electromagnetic energy. The amount of this energy, called solar radiation, that reaches the top of Earth's atmosphere averages about 340 to 342 watts per square meter. This incoming sunlight is not evenly distributed. Some places receive more, others less, depending on latitude, season, and cloud cover. The tilt of Earth's axis, 23.5 degrees, plays a crucial role in creating the seasons, causing the sun's rays to fall more directly in summer and at a slant in winter, shifting the pattern of energy across the globe. But not all solar energy is absorbed. About 30% of incoming sunlight is reflected back into space. This reflectivity is known as albedo. Surfaces with high albedo, such as snow and ice, bounce much of the sun's energy away, while darker surfaces like oceans and forests absorb more. The average planetary albedo of Earth is around 31%. Globally, just under a third of the sun's energy is immediately sent back to space by clouds, aerosols, and reflective surfaces. The remaining 70% is absorbed, about half by Earth's surface, the rest by the atmosphere, setting the stage for the complex dance of energy that drives winds, ocean currents, and weather. The atmosphere is the thin, vital shell of gases that surrounds Earth. Though it extends hundreds of kilometers above the surface, most of its mass clings to the planet within just a few kilometers. It is composed primarily of nitrogen, about 78%, and oxygen, about 21%, with the remaining 1% made up of trace gases, including water vapor and greenhouse gases like carbon dioxide and methane. These trace gases, though present in small amounts, have an outsized impact. Water vapor, the most abundant greenhouse gas, and others like carbon dioxide absorb and emit infrared energy, trapping heat in a process known as the greenhouse effect. This natural phenomenon keeps Earth's surface much warmer than it would be if all absorbed sunlight simply radiated back to space. Without the greenhouse effect, Earth would be a frozen world, inhospitable to most current forms of life. Another critical component of the atmosphere is the ozone layer, which absorbs the sun's ultraviolet radiation, protecting living organisms from harmful rays. Also present are aerosols, tiny particles that can either reflect sunlight back to space, cooling the planet, or absorb heat, warming it. The balance of these effects varies with the type and distribution of aerosols, which can originate from natural sources like volcanoes or from human activities. Just below the atmosphere lies the hydrosphere, encompassing all of Earth's water in its various forms, liquid, vapor, and ice. Most of this water is found in the oceans, which not only store vast amounts of solar energy, but also act as giant conveyors of heat and moisture. Oceans absorb sunlight, particularly in tropical regions, and then release this heat gradually. Through complex circulation patterns, ocean currents transport warm water from the equator toward the poles and bring cold water back again. This movement, driven by winds at the surface and by differences in temperature and salinity in the deep, helps to moderate global temperatures and distribute heat around the planet. Surface ocean currents, like the Gulf Stream, are set in motion by prevailing winds and shaped by the rotation of the Earth, a phenomenon known as the Coriolis effect. Beneath the surface, the so-called thermohaline circulation operates like a slow, deep conveyor belt, moving water around the world's oceans based on density differences created by temperature and salinity. These circulations not only move heat but also nutrients, carbon, and gases, supporting marine life and influencing the chemistry of the atmosphere. Intertwined with the hydrosphere is the cryosphere, the frozen water portion of the Earth. This includes ice sheets, glaciers, sea ice, and frozen ground. Though the cryosphere covers a relatively small area, it is critical to the climate system. Snow and ice reflect much of the sun's energy, contributing to Earth's high albedo and helping to keep polar regions cool. In fact, about 3/4 of Earth's fresh water is stored as ice, locked away in glaciers and ice sheets. As temperatures fluctuate, the extent of the cryosphere expands and contracts, influencing sea levels, ocean circulation, and even atmospheric conditions far from the poles. The lithosphere, or geosphere, refers to the solid Earth, the continents, ocean floors, and the layers beneath them. While it might seem static compared to the swirling atmosphere or restless oceans, the lithosphere plays an important role in the climate system. The nature of the land surface, whether it is rocky, sandy, vegetated, or covered in snow, affects how much sunlight is absorbed or reflected. Mountain ranges can influence patterns of wind and rain, redirecting air currents and shaping regional climates. Volcanic eruptions, though relatively rare, can inject large quantities of aerosols into the atmosphere, temporarily cooling the planet by reflecting sunlight. Completing this interconnected web is the biosphere, all living things from the tiniest bacteria to the largest forests. Life interacts with every other sphere. Plants absorb carbon dioxide and release oxygen, forests darken the land, changing albedo, marine phytoplankton help regulate the exchange of gases between ocean and atmosphere. Living organisms participate in the cycling of water, carbon, and nutrients, often amplifying or dampening climatic effects. For instance, widespread deforestation can raise surface albedo slightly but releases stored carbon, while healthy vegetation helps stabilize soils and moderate local climates. None of these spheres operates in isolation. A change in one can ripple through the others. Melting ice reduces albedo, causing more solar energy to be absorbed and accelerating warming. Warmer oceans may absorb less carbon dioxide, influencing atmospheric greenhouse gas levels. Shifts in vegetation patterns can change how much water evaporates into the air, altering weather and precipitation. The climate system is, at its core, a story of interactions and feedbacks. Underlying all these interactions is the principle of energy balance. The Earth's temperature is determined by the equilibrium between the energy it receives from the sun and the energy it loses to space. Imagine the planet bathed in sunlight. Of every 100 units of solar energy that reach the top of the atmosphere, about 30 to 32 are reflected away, while the remaining 68 to 70 are absorbed, split between the surface and the atmosphere. The ground itself absorbs nearly half of this energy. But energy does not stay put, it is constantly moving. Once absorbed, energy is redistributed through several mechanisms. Radiation carries energy in electromagnetic waves, the only method that works across the vacuum of space. This is how sunlight reaches Earth, and also how our planet sheds heat back into the cosmos, mostly as infrared radiation. Conduction transfers energy by direct contact, important at the interface between land and air or water and air. When you feel a warm rock on a sunny day, that is conduction at work. Convection, on the other hand, involves the movement of fluids, air, or water, carrying heat from warmer to cooler regions. Rising warm air and sinking cool air create winds and storms, while similar processes in the ocean drive currents. Latent heat is another subtle but powerful force in the climate system. When water evaporates from the ocean or a wet surface, it absorbs energy that is carried invisibly in water vapor. When that vapor condenses to form clouds and rain, the energy is released, fueling storms and redistributing heat. The transfer of energy between the surface, atmosphere, and space is not a simple one-way street. Some outgoing heat is absorbed by greenhouse gases and clouds, then re-emitted, some of it back toward the surface. This recycling of energy is the essence of the greenhouse effect. Without it, Earth's average temperature would be far below freezing. But even small changes in greenhouse gas concentrations can alter this balance, leading to warming or cooling over time. Clouds play a complex role in this energy budget. They reflect sunlight, increasing albedo and cooling the planet, but they also trap outgoing heat, acting as a blanket. The net effect depends on cloud type, altitude, and coverage, and is a subject of ongoing scientific study. Energy flows are not static. They vary with geography, weather, and time. The distribution of sunlight changes with latitude and season, as does the mix of clouds, ice, and vegetation. Volcanic eruptions can inject reflective particles into the stratosphere, causing short-term cooling. Over longer periods, slow changes in Earth's orbit and tilt can alter the amount and distribution of solar energy, driving cycles of glaciation and warming. Yet, despite these variations, the global climate system strives for balance. If more energy comes in than goes out, the planet warms. If more is lost than gained, it cools. Over millions of years, this balance has shifted, sometimes dramatically, but the fundamental processes remain the same. In sum, Earth's climate system is the product of dynamic interactions among the atmosphere, hydrosphere, cryosphere, lithosphere, and biosphere. The sun's energy fuels the system, but the way energy is absorbed, reflected, stored, and moved by winds, currents, clouds, and life determines the patterns of climate we experience. Every component matters. Each influences the others, forming a network of feedbacks that can amplify or dampen change. Understanding these foundational elements is the first step toward grasping the complexity and the beauty of Earth's ever-changing climate. Imagine Earth's climate system as a vast, intricate symphony, with each component, air, water, ice, rock, and life, playing its part. But unlike a static arrangement, the climate's melody is always changing, shaped by the constant interplay among its players. At the heart of this dynamic lies the concept of feedback, the idea that a change in one part of the system can set off a chain reaction, amplifying or dampening the original shift, sometimes in unexpected ways. This dance of feedbacks and interactions determines whether our world remains stable or tips toward a new, sometimes irreversible state. To understand how feedbacks work, picture dropping a pebble into a still pond. The initial splash is a force, a nudge to the system, what scientists call a forcing. What happens next depends on how the system responds. Sometimes, the ripples fade quickly, restoring calm. Other times, the disturbance grows, setting off waves that build instead of settling. The climate system is full of such feedback loops, some acting as brakes, others as accelerators. Feedbacks come in two main forms, positive and negative. Positive feedbacks act like amplifiers, taking a small change and making it bigger. Negative feedbacks, in contrast, are stabilizers, working to counteract change and keep the system balanced. For example, the ocean's immense ability to absorb heat acts as a negative feedback, helping to buffer rapid swings in temperature. But the climate is also full of positive feedbacks, processes that can accelerate warming once set in motion. One of the most profound positive feedbacks is the ice albedo effect. When ice and snow begin to melt, the bright reflective surfaces that once bounced sunlight back to space shrink, exposing darker ground or ocean below. These darker surfaces soak up even more heat, causing further melting, a classic runaway loop. This process is especially potent in the Arctic, where the loss of sea ice reveals open water that absorbs solar energy more efficiently, hastening the region's warming. Such positive feedbacks do not just increase temperatures, they can also trigger shifts in weather patterns and even influence the concentration of greenhouse gases in the atmosphere. On the other hand, negative feedbacks help keep the system in check. As temperatures rise, some plants may grow faster, drawing more carbon dioxide from the air through photosynthesis. This extra plant growth can help slow the buildup of greenhouse gases, acting as a brake on warming. However, not all negative feedbacks are strong enough to counterbalance the accelerators in the system, especially under rapid or large-scale change. The concept of tipping points is crucial here. In the climate system, a tipping point is like a threshold, a line that, when crossed, unleashes changes that are often rapid, large, and difficult to reverse. Feedbacks play a starring role in these tipping points. Imagine a snowball perched at the crest of a hill. A tiny push might set it rolling, and as it gathers speed and mass, stopping it becomes nearly impossible. In climate terms, passing a tipping point could mean the irreversible collapse of an ice sheet, a sudden shift in ocean circulation, or a dramatic transformation of an ecosystem. Once in motion, these changes can reshape the climate for generations. Central to the climate's workings is the greenhouse effect, a process that keeps Earth's surface warm enough for life. Greenhouse gases, including carbon dioxide, methane, nitrous oxide, and fluorinated gases, act like an invisible blanket, trapping heat that would otherwise escape to space. This natural effect is not static. It interacts with feedbacks in subtle but powerful ways. For example, as the atmosphere warms, it can hold more water vapor, another greenhouse gas, further amplifying the original warming. This water vapor feedback is a prime example of how a small change in temperature can lead to a bigger response, setting off a self-reinforcing cycle. If all carbon dioxide were suddenly removed from the atmosphere, Earth's average temperature would plunge by about 33 degrees Celsius, transforming the planet into a frozen, inhospitable world. This staggering figure underscores how central greenhouse gases are to Earth's climate. But today, human activities, especially the burning of fossil fuels and biomass, are increasing the concentrations of these gases far beyond natural levels, intensifying the greenhouse effect and pushing the climate system into uncharted territory. Clouds, too, are woven into the fabric of climate feedbacks, though their role is particularly complex. At times, clouds cool the planet by reflecting sunlight back into space, increasing Earth's albedo. At other times, they trap outgoing heat, acting as additional greenhouse blankets. The net effect of clouds depends on their type, altitude, and how they interact with other atmospheric ingredients. Some scientists note that increased cloud cover could act as a negative feedback, helping to dampen warming, while in other cases, clouds might enhance the greenhouse effect and further accelerate change. The story of albedo goes beyond ice and clouds. Surfaces with high albedo, such as fresh snow or thick sea ice, reflect most incoming sunlight. When these surfaces shrink or disappear, as is happening in many polar and glacial regions, the newly exposed land or water absorbs much more energy, shifting the local and even global climate balance. This change in reflectivity does not just affect temperature. Altered albedo can influence weather patterns, the timing and amount of precipitation, and even the release or uptake of greenhouse gases. For instance, as Arctic sea ice declines and albedo drops, not only does the ocean warm more quickly, but shifts in atmospheric circulation can alter storm tracks and rainfall far from the poles. Interestingly, changes in albedo can also complicate efforts to mitigate climate change. Some strategies, like expanding forests or increasing vegetation, may offer the benefit of soaking up more carbon dioxide. However, these darker, vegetated surfaces can also absorb more sunlight, reducing local albedo and potentially offsetting some of the cooling gains from carbon uptake. Ignoring the albedo feedback in such scenarios can lead to overly optimistic predictions about the cooling potential of reforestation or other land use changes. The ocean, covering the majority of Earth's surface, is not just a passive responder to climate change. It is a powerful player in the feedback orchestra. Oceans absorb about 90% of the excess heat generated by human-caused global warming, acting as a vast heat reservoir. This absorption helps slow the pace of atmospheric warming, another example of negative feedback. Yet, this buffering has limits. As oceans warm, they can trigger marine heat waves, disrupt weather patterns, and drive sea level rise. The ocean's color, influenced by phytoplankton populations, can change with warming and nutrient shifts, altering how much sunlight is reflected or absorbed. A subtle but significant feedback loop. Ocean-atmosphere interactions are also central to the movement of heat around the planet. These exchanges drive large-scale circulation patterns, such as El Niño and La Niña, which can swing weather and climate from one extreme to another across the globe. When ocean currents shift, they can set off feedbacks that further alter atmospheric temperatures, precipitation, and even the cycling of carbon between the sea and sky. Natural variability remains an important backdrop to these interactions. Over thousands and millions of years, Earth's climate has danced to the tune of orbital changes, known as Milankovitch cycles, that alter the amount and distribution of solar energy reaching the planet. These cycles have triggered past ice ages and warm periods, each episode shaped by the slow interplay of feedbacks between ice, oceans, greenhouse gases, and the evolving biosphere. Volcanic eruptions, too, can inject vast amounts of reflective aerosols into the atmosphere, causing short-term cooling that temporarily suppresses the underlying warming trend. Solar variability, the waxing and waning of the sun's energy output, also plays a role, though current evidence shows it cannot account for the rapid warming observed in recent decades. What sets today's climate apart is the speed and scale of change. The overwhelming scientific consensus, greater than 99% of the literature, points to human activities, especially fossil fuel combustion, as the principal cause of recent warming. Since 1750, greenhouse gas concentrations have soared by about 40%, with carbon dioxide now about 50% higher than pre-industrial levels. This is an increase far beyond what natural factors have produced over the past 800,000 years. Multiple lines of evidence confirm that the observed warming, sea level rise, and extreme weather cannot be explained by natural drivers alone. Instead, the fingerprint of human influence is clear, widespread, and intensifying. These changes are not just theoretical. The effects of human-caused global warming are already being felt, from the loss of summer sea ice in the Arctic to higher sea levels and more intense heat waves around the world. Many of these impacts are now considered irreversible on timescales relevant to people alive today. As temperatures, rainfall, and sea levels continue to shift, the risk of damage from natural disasters is expected to rise, with consequences for ecosystems, infrastructure, and economies. The interplay of feedbacks, both positive and negative, means the future path of climate change is highly uncertain and could unfold in non-linear, sometimes abrupt ways. Some trends, such as the decline of Arctic ice or the acidification of oceans, may already have crossed or be approaching tipping points, with changes that cannot easily be undone. Other aspects, such as the response of clouds or the full impact of ocean warming, remain areas of active research and debate. What is clear is that the choices made today will shape the climate of tomorrow. Reducing greenhouse gas emissions is essential to limit further warming and avoid the most severe consequences. Climate models, which incorporate our best understanding of the system's feedbacks and interactions, project that continued emissions will bring more extreme changes, while swift action can help stabilize the system and preserve a more livable world. In the end, Earth's climate emerges from a tapestry of interactions, each strand connected to the next, each feedback capable of shifting the balance. The story of our climate is one of both resilience and vulnerability, of forces that can stabilize or destabilize, and of a planet whose future depends on the delicate equilibrium of its many parts. Climate is not a static backdrop to the story of life on Earth. but a restless, ever-evolving force shaped by a combination of grand celestial cycles and the ceaseless churn of processes both above and below the surface. Natural variability has always defined Earth's climate, with patterns and pulses that range from the scale of seasons to spans of tens of thousands of years. Yet in the present era, the climate system faces unprecedented disruption, one unmistakably and overwhelmingly linked to human influence. To understand how the climate can change and why it is changing so rapidly today, it helps to first consider the drivers of natural variability. Some of these forces are embedded in the very architecture of our planet's journey through space. Among the most influential are the cycles described by Milutin Milankovitch in the early 20th century. These Milankovitch cycles refer to regular, predictable changes in Earth's orbit and tilt. The orbit, or the path Earth traces around the Sun, periodically shifts from more circular to more elliptical, a rhythm known as eccentricity. Meanwhile, the angle of Earth's axis, its obliquity, wobbles between about 22 and 24.5 degrees, altering how directly sunlight strikes different latitudes. Finally, there is precession, a slow, top-like wobble that changes the timing of the seasons relative to Earth's position in its orbit. Each of these cycles unfolds over tens of thousands to hundreds of thousands of years, gently modulating the amount and distribution of sunlight reaching the planet's surface. These orbital shifts are powerful enough to drive vast swings in climate, triggering the advance and retreat of ice ages and shaping the rhythm of glacial and interglacial periods. When the cycles align in certain ways, they can tip the balance, leading to the gradual buildup or melting of great ice sheets. Yet, for all their influence, these cycles are slow, relentless drummers in the background, not the cause of the abrupt warming the world is experiencing now. Scientists have examined the timing and magnitude of past cycles and found that Milankovitch cycles cannot account for the rapid temperature rise of recent decades. The current speed and scale of change are simply out of sync with these ancient patterns. Adding further complexity to Earth's climate variability are explosive events that erupt with little warning. Volcanic eruptions, for example, can hurl millions of tons of aerosols and ash high into the atmosphere. These fine particles scatter sunlight, acting like a temporary sunshade and causing the planet to cool for a year or two. The effects, though dramatic, are usually short-lived. The particles eventually settle out, and the climate resumes its previous course. Solar variability, the subtle waxing and waning of the sun's energy output, also leaves a faint mark on the climate. Sunspots and fluctuations in solar radiation can nudge temperatures up or down, but the magnitude of these changes is dwarfed by the transformations underway today. Cycles, eruptions, and solar shifts. These are the natural architects of climate's ancient variability. For millions of years, they shaped habitats, guided migrations, and set the tempo for the rise and fall of species. But as the 20th century gave way to the 21st, the climate system began to move to a new and unfamiliar rhythm. What stands out now is not just that the climate is changing, but that it is changing with a speed and scale that natural drivers cannot explain. The evidence pointing to a new architect, human activity, is both broad and deep. Since the dawn of the industrial age, the burning of fossil fuels and the clearing of forests have released vast quantities of greenhouse gases, especially carbon dioxide, into the atmosphere. These gases act as an invisible blanket, trapping heat that once would have escaped freely to space. The numbers tell a clear story. Greenhouse gas concentrations are about 40% higher than they were in 1750, and carbon dioxide alone has risen by roughly 50% over that time. This increase far exceeds the natural fluctuations seen in the last 800,000 years and is closely linked to the consumption of coal, oil, and natural gas, as well as widespread deforestation. Multiple lines of evidence converge on the conclusion that this new force, anthropogenic or human-caused climate change, is now the dominant factor shaping Earth's climate. The Intergovernmental Panel on Climate Change, drawing on the work of thousands of scientists, has stated with at least 95% certainty that human activities are responsible for the majority of recent warming. In fact, the most recent comprehensive assessments find that human influence on the climate system is unequivocal. The consensus is overwhelming. More than 99% of peer-reviewed studies agree that greenhouse gas emissions from human activity are the principal cause of the warming observed since the late 19th century. Since 1850 to 1900, the planet has warmed by approximately 1.1 degrees Celsius, with most of that increase occurring over the last few decades. This may sound, at first, like a small shift, but it is enough to unsettle the finely tuned balance of the climate system. The warming is not uniform. Some regions heat faster than others, and the impacts cascade through weather patterns, ocean currents, and the distribution of life. The rate and extent of this change are exceptional, outpacing anything seen in the records of natural climate variability. The implications are already visible across the globe. Sea levels are rising as glaciers and ice sheets lose mass. Heat waves are growing more intense, and the frequency of extreme weather events is increasing. Some effects, such as the loss of summer sea ice in the Arctic, are now considered irreversible on timescales relevant to people alive today. Species shift their ranges in search of suitable climates, and ecosystems feel the strain of altered temperature and precipitation patterns. The fingerprints of human influence are not limited to temperature. They are etched into the chemistry of the oceans, the behavior of the atmosphere, and the structure of landscapes. It is not just the physical world that is affected. Climate change carries profound consequences for human societies. Rising seas threaten coastal communities, while more intense storms and shifting rainfall patterns increase the risk of floods, droughts, and wildfires. The financial system, too, faces growing uncertainty, as climate impacts can be highly nonlinear and unpredictable in their timing and severity. The ripple effects touch health, food security, infrastructure, and economies, often amplifying existing inequalities and vulnerabilities. Despite these mounting risks, the future remains open to influence. The trajectory of climate change from this point forward is not fixed. It depends on the choices made today. Climate models, drawing on the best available science, project that continued high emissions will bring more severe and disruptive changes. However, if greenhouse gas emissions are reduced, if the world acts to limit the flow of carbon into the atmosphere, the pace and magnitude of future warming can be slowed. The actions taken now will shape not only the climate of the coming decades, but the legacy inherited by generations yet unborn. There is, nonetheless, a sobering element to this story. Some of the changes already set in motion are, for practical purposes, irreversible. The loss of ice sheets, the rise of sea levels, and the acidification of oceans represent long-term shifts that will persist for centuries or longer, even if emissions were to cease tomorrow. Yet many other impacts can still be moderated or avoided entirely, depending on the resolve and cooperation of the global community. The scientific consensus on these issues is not a matter of opinion, but the result of decades of painstaking observation, measurement, and analysis. The national academies and other leading scientific bodies have reviewed the evidence and concluded that greenhouse gas emissions from human activities are the primary driver of current and future harm to climate, health, and welfare. The IPCC's most recent reports, drawing on data and modeling by experts worldwide, underscore that human-induced climate change is widespread, rapid, and intensifying. As humanity confronts this new chapter in the story of climate, the stakes are clear. The forces of natural variability, Milankovitch cycles, volcanic eruptions, solar shifts, will continue to play their part, but they are no longer the main actors. Human activity now dominates, propelling the climate system into a state for which there is no close parallel in the geological past. The evidence is not only compelling, it is urgent. The world stands at a crossroads, with the opportunity and the responsibility to shape the climate future. The legacy of this era will be measured not only in degrees of warming, but in the choices made to protect the stability and resilience of the climate system upon which all life depends.